Okay, we're going to talk about binary. And essentially, binary is a system for inputting and outputting to computers. Okay, so think about it as we have inputs that go into computers, and then a computer outputs something. Okay, in math, this is a common. If you guys grade 11, yeah, in grade 11, if you guys have gone to your math, you might think of f at x as a function, where x is the input of the function and f at x is the output of the function. Computers run off that, hence why we have programs that are generally called functions. When we build our own little program within a program, they usually call it a function. So binary is a little different from what we're used to. We're used to numbers being listed from 0 to 9. 1, 2, 3, 4. I almost forgot what came after 4 there. Okay, this is a decimal system. Okay, decimal means deca, which is 10. So there are 10 digits in here. So if we were to actually do the cardinal numbers, which is the counting of a system, the cardinal numbers here are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 digits, but be aware that, and we talked about in computer science too, we start at 0, 0 being one of our digits. Technically, the number 10 is a combination. There are two place values. It's a combination of the digit 1 and 0 to create 10. Okay, so this was the cardinal, which is the counting, but the actual numbers here, there's actually 10 digits and they run from 0 to 9. Binary, on the other hand, okay, a binary system only has 2 digits. The 2 digits are 0 and 1. If we do the cardinal counting, that's 1 and 2. Those are the only 2 things that machine code, so when we input machine code for a computer, the computer actually reads things. That's a terrible spelling of computer, but it actually only reads things like this, for example, just zeros and ones. And the reason computers are built that way is because we use electronics. And what's good about an electronic system, you're usually either off or you're on. Okay, so what that means is we can communicate with computers by using switch systems that are either on and off. And usually 1 represents something being on and 0 represents something being off. We can represent all the numbers in a decimal system technically with binary. Okay, now this is where it becomes a little bit confusing. So we'll talk about the place values. Place value becomes very, very important. In a decimal system with place value, let's do binary in green from here on in, and we'll do, I guess, decimal in red. When we have place values, okay, when you think about it, you essentially run from the 0 to 9 in this place value and 0 to 9 in this place value. From here, I can represent numbers all the way up to 9. This is called the ones, right? We're used to this in the tens, okay? This concept here is it can go from the numbers 0 to 9. So I can be as low as 0, or I can go all the way up to the number 9. And in the tens column, same concept. I can have 0 tens, or I can have 9 tens. So within 2 place values, I can represent 99 objects, okay? Binary place value is a little bit different. And I do want to show one other thing. Think of exponential values here, okay? If you think of the numbers, let's say, this is essentially 10 to the power of 2 in terms of the number we can represent, and 10 to the power of 1. We can represent 10 digits in the ones column. And remember, those reason we can represent 10 digits is because we start at 0. 0 to 9 is actually 10 numbers. So how many digits? Well, that's 10 to the power of 1. Once we add a second place value, I know this is very mathematical at this point, so this might be one of the confusing pieces to it. 10 to the power of 2, remember, that represents 100 numbers. We can represent from 0 to 99. So we count 0 a lot in computer science. That's actually 100 digits. Okay, so that's kind of a little history of our decimal system. But what about a binary system? Well, a binary system, I can represent 0 or 1. That's only 2 digits, okay? So if we think about how many numbers I can represent 2 to the power of 1. Well, let's put 2 place values. Well, from here, I can now go a 0 or a 1. Well, how many numbers is that? Well, it gets a little harder. We know decimal system. We're so used to counting. It's very easiest for to describe this. So when we describe numbers, we describe them in the decimal system. But it doesn't mean that we're not still using binary. So how many decimal numbers, or how many cardinal numbers can we represent with 2 place values in binary? Well, that can be told by taking 2 to the power of 2. Well, what are they? Anyone know what 2 to the power of 2 happens to be? So we can represent 4 numbers. So what are these 4 numbers? Well, let's list them here. In my 2 place values, I can say there's 0, 0, and that may be with ASCII what 0 represents. I can represent 0, 1. Okay, maybe that represents 1. I can represent 1, 0. That may represent the number 2. And then I can represent 1 and 1, which actually represents the number 3. It looks like we're only counting the 3, but again, remember there's 0. So we have 0, 1, 2, 3. That's 4 values. So for every place value we add in binary, essentially what we're doing is we're taking the power of 2 and moving its exponent up a value. Okay? 2 to the power of 3, that means we can technically have 8 values here. Okay? Here we can go 2 to the power of 4, 2 to the power of 5. And this is this doubling idea. My son is very into doubling these days. He's a young guy. 2 to the 6. And they can look at this. We now have 64. And you remember we start talking about 64-bit systems, 32-bit systems. They play right along these binary codes, right? We actually are doubling base 2 when we talk about number systems. So let's jump to a new page here. Okay. So if I have a binary system, okay, and I have 3 place values, my question to you guys is going to be, how many numbers can I represent? And once I write out those numbers, what might be their representations in binary? So Albert said 8. That's right. Think of it again. We have 2 to the power of 1 for 1 place value, 2, and then 2 to the power of 3, which means we can represent 8 numbers. Let's try to write out all 8 of them. Want to help me out? So what might be my first combination?
0, 0.
Yeah, 0, 0.
0.
0, yes. So we have 3 place values. And if we're going to count in decimal, okay, so think about it as this is decimal right now, and I'll make a little space here. Let's erase this 8. We're going to call that binary. We know that this is 8. I'll place it here. We'll call this the binary representation, okay? So there's our binary to decimal. What number might that represent in decimal?
0.
0, okay. What's my next one?
0, 0, 1.
Okay, and what does that give us?
1.
Yep, keep going.
0, 1, 0.
Yeah.
2.
Yeah.
0, 1, 1.
Uh-huh.
That's 3.
Yeah.
1, 0, 0.
Yeah.
I'm guessing that's 4.
You're right. Keep going. You're doing great.
1, 0, 1.
Yeah.
Which is 5. And then 1, 1, 0.
Yeah.
Which is 6.
Mm-hmm.
And then 1, 1, 1 is 7.
Okay. But I only got to 7. You told me there was 8.
But it includes 0.
Very good. Excellent. Way to catch that. Awesome. So that's exactly it. So a binary system is we still, in our counting system, we refer to our numbers as 1, 2, 3, 4, 5, 6, 7, 8, 9. Binary doesn't refer to it that way. It's either 1 or 1, 0 or 1, 1 or 1, 0, 0. Everything's ones and zeros, and that's how computers take information. That's the basis of machine code. We don't write our code that way, okay? Our code, well, I have a little thing, is an abstraction. Okay. An abstraction is, for instance, if we're going to be writing in C for our class or in Lua, okay, we have some code. Maybe there's some syntax to it. So you say my int void, or int main, sorry, I should say. That's the usual for C code, int main void, or maybe we were writing something in Lua. We have, for C, we have something called a compiler. And the compiler takes my source code and does a conversion, okay? Think of it like an input and output. My source code goes in and it turns it into a machine code. And that machine code is written as a bunch of stuff like this. I'm just giving an example. I don't know exactly what it is. Okay, and this is how our computer understands things. So computers understand binary systems. Okay, and essentially what's neat about these binary systems, because numbers can go on forever, which, you know, practically means they're infinite. Now our computer sizes are infinite. We don't have that. But because numbers are kind of infinite, we can represent all kinds of different things with these. Okay, so maybe as you go to watch part of that lecture there, and it'll get into it, you'll start to notice that you can represent A's and B's using binary numbers. So on the previous page, we only went up to the number 8 here, but I could keep going with those binary representations. But then maybe eventually get to, I don't want to do decimal numbers anymore. I want to use characters. I want to use characters of the alphabet. Or I want to use characters like this. What is this thing called when you see it on a computer? Anyone know? I know it's not a great representation.
Emoji.
Yeah, an emoji. Binary code. Emojis are converted into binary code. There is some code that's widely accepted in machine code that gets put in, and the computer understands that, oh, they're looking for this symbol. I'm going to output this emoji symbol in this case. Okay.